Okay. And that looks good. Okay.
Okay. Our speaker for tonight is our own Brad Hoehne. Brad's a past president of the Columbus Astronomical Society, and he is presently the director of the John Glenn Astronomical Park, Astronomy Park in Hoehne Hills. So, and his topic for tonight is how the universe got big, a history in 4 objects. Okay, Brad.
Thank you, guys. I have a tendency to go long, so what I'm doing is I'm setting up a timer here to remind myself of how long I go. So doesn't necessarily mean I'll be short. So this talk came out of an idea that I had a couple years ago. I was visited at the John Glenn Astronomy Park by this lovely young lady who was extremely enthusiastic about astronomy, and she knew a lot of really cool stuff about astronomy. She knew that the planets were other worlds. She knew that there were galaxies out there made of thousands and millions and bajillions of stars, I think is the way she put it. She knew that black holes existed. She had a very rough idea that space was really, really big. And it occurred to me that this little girl had on her t-shirt more information than just about every human being had about the universe until maybe about the time of Galileo. They knew she knows on her t-shirt that the stars are other suns. She knows on her t-shirt that the planets, those wandering dots of light in the sky, are in fact other worlds and not just luminiferous bits of cosmic ether up there in the sky. And so what I wanted to do was take people on a journey into the past and ask you to strip away all of your modern knowledge about the universe and just experience the universe from the ground up, as if you were standing on the plains of Africa 200,000 years ago, looking up at the night sky, and then build back up the universe from square one. Now, the problem with this is that's a lot of stuff to do. It would take weeks. Now, I could do that, but it would take weeks to go through the highlights of the history of astronomy. So what I wanted to do was reconstruct the history of astronomy in a very limited fashion. I wanted to reconstruct it by telling the history of how the universe went from being a small thing to being a very, very big thing on the backs of 4 celestial objects. And so let's start off with the way the universe looked to us 200,000 years ago. You could dress someone up from the plains of Africa 200,000 years ago, put them in a suit, put them on a subway. They would look exactly like a human being today. They would have the same amount of intelligence. Perhaps they would have even more intelligence because they had to use their wits to survive. What did they see the universe as? Now, if you've gone out into the Hoehne Hills and observed the night sky, you can see the Milky Way. You can see the stars. You can see that the stars are different brightnesses. There's this milky band of light across the sky, which we know to be the Milky Way. And one thing that you can sense just by looking at it is that it's very far away. How far, we don't know. But it's a lot further away than the trees and the horizon around you. How do we know that? We can walk around from place to place, and we don't actually see the stars moving from side to side. They remain fixed in the heavens. So that is the first thing that people knew about the heavens. The heavens are vast and very, very far away. They didn't know much else. Ooh, zapped. Now, you could, if you wanted to, pay really close attention to the sky, and after a little while, you would begin to notice that some of the stars in the night sky actually moved around from night to night. These are 2 planets right here. Anybody know what those are? It's from a couple years ago. This is Jupiter and Saturn, so from a little while ago. And you would actually notice that they were wandering. Now, you couldn't tell that they were anything other than just really bright stars, but they had this special property. And the Greeks, way back when, named them the wanderers. The word for wanderer was planetos or planeta, and that is where we get our word for planet. But at the time, it just meant something that was wandering. They did not have the conception that that little girl had on her t-shirt. I'm going to decharge myself. The other thing they would notice is that the stars rotated around. And in fact, if you paid really close attention, they rotated around once each cycle of day-night. Basically, the heavens went around us in what we now call 24 hours, what they would have just called a day. So there was a sense of the motion of the sky in another way as well. And then finally, there were occasional little things that would enter into our consciousness. Little changes would happen to the heavens. We would get meteors and that kind of thing would appear in the night sky. But our conception of the heavens was not very much more sophisticated than that. Now, people several thousand years ago were not much different than people 200,000 years ago. And we do know that they were, in fact, looking at the heavens. We know, for example, because of things like this. This is the Nebra sky disk. It was actually found in Germany. It's thought to be between 5,000 and 7,000 years old, which is pretty, they call that Neolithic. This is before most human history existed. This is very, very early. And interpreting this as the moon, the full moon, and maybe the Pleiades or something like that. But clearly they're looking at the sky. They are actually paying attention to it. Now, not long after that, great civilizations grew up around the Middle East and the Nile Delta. You had some civilizations in Turkey and Iraq, and a really big one in Egypt, the Egyptian civilization. They started to look at the sky. How do we know? Because they put it in their writings in their tombs, which exist to this day. This is actually the tomb of Senmut, one of the pharaohs, and it's on the ceiling of his tomb. This is actually a star chart. This is actually a map of the different heavens. And my favorite constellation, the one that I actually know is part of the Egyptian pantheon, is this one here, which you've probably seen in Cosmos. This is Ursa Major, as viewed by the Egyptians. Now, in case you can't see what's going on, this is a hippopotamus with a crocodile on its back.
Obviously.
Yes, obviously, it looks just like that. This is a bull and a reclining man with an aten on the top of his head. So this is how the Egyptians actually viewed it. So at that time, people were knowing enough about the stars to actually make pictures out of the heavens. They knew that they came back around from year to year. They knew enough about them that they embodied them in their death rituals and that kind of thing. So people were starting to pay attention to the heavens. And then finally, people started to get some small quantitative sense of the size of the world and the universe, in a sense. And a very famous Greek scientist in about the year 300 BC or so, Eratosthenes, figured out in a very interesting historic way how to measure the size of the Earth. Basically, he took a stick and noticed that at a certain point in a city called Syene, that the stick cast no shadow on the longest day of the year, summer solstice. And then up in Alexandria, the stick cast a very definite shadow when it was vertical on the same day. He was the director of the very earliest incarnation of the Library of Alexandria, and so he managed to hire a guy to actually walk from Syene to Alexandria, which works out to about 800 kilometers, and figured out that the angle that this represented was about 1/50th of the angle around the planet, and then if you multiply 50 by 800, you get about 40,000 kilometers, which is a very close estimate of the size of the Earth. So even back before zero, back before in the very early Greek days, people did get a reasonably good sense of the size of at least the Earth.
I thought it was still flat then.
It was. No, it only became flat recently in the age of the internet. So let's start there. That's the context. Our first object, to talk a little bit about the history of the universe, is the moon. The moon is the brightest object in the night sky. It goes through phases. It's rather interesting to look at from the ground. And to show you how sophisticated people were in those days, they were actually able to get a very rough estimate of the distance to the moon. You could do what's called parallactic measurement. You could take a measurement in one part of the world, and then take a measurement of the moon in another part of the world, and the moon will actually be in a slightly different part of the sky if you take measurements at the same time. And they got a rough estimate of the moon. And a guy named Aristarchus who figured out, now here's what you could actually see on the surface of the moon. This is actually what a naked eye view, that's about my estimate of how sharp the moon is. So we didn't really have a good sense of what the moon was, but, hello, you know what, I skipped ahead in my talk, but other societies, other civilizations actually figured out quite a lot about the moon. One of them was the people in North America that lived in the Newark part of what is now Ohio, were so sophisticated in terms of figuring out the cycles of the moon that they were able to figure out what is called the most northerly moonrise, which is the point along the horizon that the moon is most north when it rises. Now, it actually occurs, that particular moonrise occurs about every 18 years or so. So if you want to figure that out, you have to pay attention to the skies for at least 18 years. This is an extremely sophisticated society. And this particular mound right here, actually still exists. You can watch the moon rise when it gets relatively close to the most northerly moonrise. Last time it happened was in about 2011. So other societies in Europe and North America also figured out the most southerly moonrise, the equinoxes. They figured out the locations and movements of the sun and moon. They were paying attention to this enough to embody it in their architecture. Here's a map of how far north the moon actually goes each cycle around, and you'll notice that it peaks up and then it goes back, and then it peaks up and then it goes back. It's actually really difficult to figure out the most northerly moonrise because it's not consistent. It doesn't just go farther north each time. It kind of makes this little wobbly thing. And in order to figure that out, you would have to pay attention for at least 18 years and hope that on the night of the most northerly moonrise it wasn't cloudy, which would be terrible. Then you'd have to wait another 18 years to figure it out. So here's the peaks, and right around here is when you get the most northerly moonrise, and this is when you get the most southerly northern moonrise. Another society that seems to have done this were the people that built the medicine wheel in Wyoming. This is about 10,000 feet above sea level up on a beautiful ridge. Depending on who you ask, it's either 200 years old or 10,000 years old. I tend to think it's a little bit somewhere in between. It's been maintained for a long time, but it has alignments with the solstices, the equinoxes, and this is the most northerly moonrise. So now, societies began to start to take notes of not only the moonrise and that kind of thing, but they also began to take notes of other things. The Babylonians started to take notes of the positions of the stars, and in particular, the appearances of various comets. This is a cuneiform tablet. It's actually a copy of a more ancient tablet. This one is from 164 BC, which is right around the time when they last started using cuneiform. Cuneiform had died out by about that point. But this is records from about 1,000 years before that. So people really got started early in taking records, making records of the sky. This particular tablet is called the Mul Alpin tablet, and there's lots of astronomical information. Can't you tell? In this particular tablet, one of the most important things is they tracked the lunar path through the heavens, and they were able to use that in order to predict eclipses, and not just lunar eclipses, but solar eclipses. Can you imagine that on any given place on Earth, there's an average of about one solar eclipse every 300 years or so, on average? So in order to figure out that there are solar eclipses, you would have to take records from a very wide area of the Earth in order to figure out whether or not the records of solar eclipses. You would have to actually be very sophisticated in your data gathering. So they were very good at it. They also had the phases and the rising and setting times of the moon. They figured out a lot of information on this. And they were able to figure out the paths of solar eclipses ahead of time and make predictions about that. The Greeks used the moon to figure out, gave the first rough estimate of the scale of the universe. And this guy, Aristarchus here, had a rather interesting way to try to figure out how far away the sun was from the Earth. And the way he did it was this. He actually imagined that there comes a point in time when the moon is exactly a half moon. You get the Terminator going straight down the middle, like this, not like this. And at that time, if you could measure the angle from the moon to the sun, you could actually figure out how far out that way the sun had to be. So if the sun was really close and the moon was a half moon, the moon would actually have to be tilted a little bit forward in order for it to be a half moon. I mean, think about it this way. If the sun were here and the moon were up here, you'd actually be seeing the moon nearly full if it's close. If the sun is infinitely far away, the half moon would be precise at 90 degrees. You would have a perfect 90-degree angle at that point. And so he was able to deduce, very, very roughly, that the angle between the sun and the moon, when he judged the moon to be a perfect half shaded, was about 87 degrees. In other words, the angle of the width of the sun to the moon here, this angle here, would be about 3 degrees. And using a little bit of trigonometry, which they could do in those days, he figured out that the sun is somewhere between 18 and 20 times as large and as far as the moon. Why is it larger and as far as the moon? Because it appears the same size in the sky. So you figure that it's going to be 18 to 20 times as far away, also 18 to 20 times as big. So the sun was a lot bigger than the Earth, per his reckoning. Now, the real answer is that the sun is about 400 times further away. The problem is, it's really difficult to judge when the moon is a perfect half. First of all, the surface is very rough. You know, the terminator, the line between night and day, is kind of blurry. He kind of guesstimated it. But he got a good idea that the sun was a lot further away and a lot bigger than than the Earth and the Moon, or at least the Moon. So that was one piece of information about the scale of the universe. The universe was pretty big. It was a lot bigger than the Earth, a lot bigger than the Earth-Moon distance. So the second object we're going to take a look at. Now this is going to take you into some areas that today we can look back on and sort of laugh at the people, because they had some rather preposterous ideas. And these ideas about, for example, the planets, the planet Venus and the other planets, lasted a very long time. And in fact, the dominant model of the universe, the model of the universe that is most successful, is the one I'm going to tell you about now, is the model of geocentrism. That model has lasted longer than any model in history, basically. At almost 2,000 years, this particular model was dominant. Now, it may seem preposterous to us that everything in the universe is going around the Earth. But they had good reasons to think that. And I'm going to take you through their way of thinking to kind of give you an idea of how extraordinary it was when we finally broke free from that. So let's take a little journey into our history of the way we looked at the solar system. So first of all, Venus, to the ancients, was not a planet, as I was telling you earlier. It was, in fact, just a little disembodied light in the sky. And, interestingly enough, for a long time, in some of the earliest records, it was not just one light in the sky, it was two lights in the sky. They had a morning, or let's say west, that's an evening, and a morning. They did not know that this bright thing in the sky was the same as this bright thing in the sky. And it was a lot like this situation. Yeah, I mean, the one guy is never in the same place as the other one, but let's get to those Babylonians. And I'm not even going to attempt to pronounce this name. I think I will. Amisadukwa. The tablet, this is another one of these cuneiform tablets. This was from the 7th century BCE, and it covers a period that was probably about 1,000 years before that. So around about 1,700 years before our calendar starts, people started to figure out, maybe Clark Kent and Superman are the same thing. So this is a tablet that actually seems to show evidence of that. Fast forward a millennia or so, and people were watching the heavens and trying to develop a model of the universe. The most influential person in history when it came to developing a model of the universe was this guy, Aristotle. Now, you've probably heard of Aristotle. Aristotle was, to a certain extent, he wasn't really a scientist. He wasn't really a philosopher, so to speak. He was kind of like an encyclopedist. Basically, he collected ideas from around the world and around the empire, and he judged which ones he liked the best. There were certain ones that he thought were good and certain ones that he thought were lacking. And he developed these theses that he would publish, and they became extremely influential. Now, there's a reason why they became extremely influential, opposed to the theses of this guy, for example. We're getting back to Aristarchus. Aristarchus had a completely different model of the universe. Aristotle saw the universe as being the earth at the center of the universe. Above the earth were these various heavenly spheres, these crystalline spheres that gradually wrapped around the earth. You've probably seen this model before. The lowest sphere was the one that the moon was on. The higher sphere, you had Mercury, then Venus, then the sun, and then you went outward, Mars, Jupiter, Saturn. And then beyond that, you had the stars. Beyond that, you had the constellations, the actual zodiac constellations, and then beyond that, you had the primum mobile, the prime mover. Basically, that was some entity that got the whole thing started. Aristotle's model of the universe was that this whole thing was spinning around the Earth. The primum mobile moved the stars and the constellations once around the Earth every day, 24 hours. As you went in, the model of Saturn, which was close to the prime mover, got dragged along with it, got dragged along with the stars. So it moved almost as fast as the heavens. So it would generally, from year to year, Saturn, as we know, is here one year, is here the next, is here the next, and it takes a couple of decades to go around the heavens. When you get further and further in, and as you get farther and farther from this prime mover, the dragging effect, the friction, so to speak, with the firmament actually gets less and less. And that's what causes the planets, the wanderers, to in fact move faster and faster as you get in, because they're not getting dragged around once a day. They're getting dragged a little less than once a day, and they move a little bit less. And that's what, according to Aristotle, explains the motions of the heavens, was this dragging effect. And then as you went further and further in the crystalline spheres, they weren't perfectly free of friction. They actually got dragged along, and that's what made the heavens move. Now, Aristarchus had a different model for different reasons than we would expect today. He put the sun at the center of the universe. That was what's called the heliocentric model. Now, his logic was not that this solved the motion of the heavens well. His logic was that it didn't make much sense that something small, like the Earth, moon system, would be orbited by something really big like the sun. He thought the sun is bigger, therefore it's more important, therefore the Earth goes around. That was his logic. Now, people liked Aristotle a lot more for several reasons. First of all, Aristotle, his belief in the universe was that the Earth was fixed at the center of the universe. Now, if you close your eyes and try to feel the Earth moving, I'm not feeling it. Can you feel it? Can you imagine? Waiting for that to go. Thank you. Is it going? That's good. Okay. So, can you imagine in the ancient world every mode of transportation that you would ever be on? An old rickety cart, a boat on the ocean. If you're walking across a mountaintop, everything would involve forces that you could feel. You would feel the wind in your face. You would feel the motion. They could not conceive of an Earth that you could not feel moving. If the Earth were going about the sun, to their mind, the idea was that the Earth moved. Now, we know, of course, that inertia is part of this whole thing today, and that's not the way we think today, but it made some sense. Now, there was another reason why people bought into Aristotle and not Aristarchus, and that was authority. Authority in this guy. Anybody know who that guy is? This is Alexander the Great. And Aristotle got his authority because he taught Alexander the Great. He was the tutor of the young Alexander the Great. The king at the time said, I have this young, talented son. I would like the greatest, most knowledgeable person in the empire to come and teach him to be a man. And part of that was learning about the universe and that kind of thing. So Aristotle taught Alexander the Great, and Alexander the Great then went on a few years later to conquer half the known world. That's a pretty good endorsement. So Aristotle won out for a couple of good reasons. There are others, as we will see. So, Aristarchus got forgotten about. His writings are largely lost. We have fragments that were discovered and reconstructed over time, but most of the writings of Aristarchus are gone. We know them indirectly from other sources mostly. So, the other reason why Aristotle had a kind of cachet, so to speak, is that the rest of Aristotle's model of the way the universe worked was very consistent. They had all of the ideas of Aristotelian physics kind of fit together. Aristotle normally would compile ideas from a bunch of different people. One of the ideas came from a gentleman by the name of Empedocles, who lived a little while before him, and Plato, who was his student. He combined them into a model of the universe, which he published, which saw the universe as made up of 5 different substances. All matter was made of, and you probably know them from seeing sci-fi movies, earth, fire, air, water, and then to the heavens, he relegated a final substance, which was called the 5th substance, the 5th essence, and if you translate that out into his language, it was the quintessence. That was the 5th essence that he gave to the heavens. And so this particular model also fit into his cosmology. And because things went together very well, people kind of paid a little bit of attention. He crossed his I's and dotted his T's really well. So here's his model of the different substances. And Plato had actually been part of a group that was taking data from people like Pythagoras, and those people discovered that there were, using mathematics and logic, that there were 5 perfect regular solids. Well, if there were 5 perfect regular solids, and if Aristotle says, hey, there's 5 individual substances, that's gotta mean something, you know? They also attributed colors to each of those substances, and they attributed certain qualities of being to each of these substances. So fire, the substance, wanted to go up. It wanted to rise quickly. So something that had a lot of fire in it would go up. If you heated something, it would go into the sky. When you burnt something, it would go into the sky. It's logical. It makes sense, right? Water wanted to seek lower levels. So if you dropped water, it would flow and it would go downhill, flow into the ocean, go to its lowest possible level. That was the quality of water. Earth is pretty easy. It wanted to fall to the earth. Earth was the base of all things. You know, it wanted to go down. So if something had a lot of earth in it, you know, you had a lead bob, it would be very heavy because it had earth in it. Air wanted to float gently upwards. So if, they didn't have helium in those days, but if they did, they would consider helium to be the essence of air. That is air. And then finally, they looked up in the heavens and they saw these spheres moving around their heads, and they said, that is unlike anything that we see here on Earth. This spinning motion around the Earth doesn't correspond to anything we see here on Earth. Plus, it's perfect. The stars come back year after year, that they seem to move in these beautiful circles. And so the idea that they attributed to the ether, the quintessence, was that the heavens moved in perfect circles. The other idea that they had, and this one won out a lot of people in later days, was that the 4 main elements, earth, air, fire, water, those were somehow lesser elements. They were somehow lesser elements, and somehow they were corruptible. They weren't They weren't pure and beautiful and not of this world like quintessence was. Excuse me, I'm going to get some water. So one of the things they thought of with respect to everything around you, their existence, people get dirty. If you take a measurement of the weight of something, you don't get a very accurate measurement. The weather is unpredictable. Human bodies break down, we die. Animals smell bad and everything like that. The things of this earth were somehow lesser than the heavens. The heavens were pure and amazing, and the earth down here below was corruptible and just not great. If you wanted to know the essence of the universe, the way to get at the essence of the universe was not to study earth, air, wind, and fire. Earth, water, fire, and air. It was to merely think about it, to deduce logically. So, in contrast to that, the heavens were incorruptible. They were pure. The only way you could get at them was to actually consider them in your mind logically. And another idea that Aristotle had about how you understand the universe was, he said that in order to have a knowledge of a thing, you have to actually grasp its cause. You have to explore the thing in several different ways. And the different ways were the material cause. You had to actually figure out what it was made out of. The formal cause, which was the skill that you used in order to deduce, to have that thing happen, or the skill that you used to figure it out. The efficient cause was the design and the plans, and the final cause was why this was all done in the first place, what it was for. So if you wanted to talk about the heavens, the material cause of the heavens, well, what is the material cause? It's quintessence, just made that way. The formal cause was, well, the prime mover did it. That's it. The efficient cause is, well, the prime mover designed it. And the final cause was, well, some ineffable something that we're meant to learn from it. So basically, they had a philosophy based on the thoughts of Aristotle. These were all put together, and they were all very consistent. If you took any one of them out, the edifice would fall down. And this particular way of thinking actually lasted a really long time. In fact, people taught it in college in Europe. Most of the most ancient colleges, Cambridge, Oxford, which got their start in medieval times, the colleges in Spain, which were started during the Moorish era, in the 11th to 14th century, they all taught this. And it was so prominent that even a guy like, this is supposed to be Isaac Newton in his later days, practiced some of the principles that he learned from earth, water, air, and fire, and ether. He wanted to learn the essence of that. Chemistry grew out of this. People inadvertently would discover the way the world really worked by trying to explore the material nature of the world in this way. And it was long after Galileo, Isaac Newton was still attempting to explore the world in this way.
I'll give you a fun fact.
I'm sorry?
I'll give you a fun fact.
Okay.
My father was born in 1895. Rural part of Greece, up in the mountains. He was taught this.
Yeah.
He tried to teach me this.
Yeah. Yeah, I mean, it was very enduring. So it went from the time of Aristotle, 300-ish BCE, to almost the modern era. It was extremely dominant. Yeah. So just to remind you once again, the prime mover spins everything, and then these other layers get dragged along, and that kind of thing. But here's the problem with that model. If you we're amateur astronomers. If you pay really close attention to the movement of the heavens, I mean, yeah, Mars was over there a couple months ago, and now it's over there. So yeah, okay, if I'm paying just a little bit of attention, it does kind of look like Mars did this across the sky. You know, Jupiter was in Sagittarius a couple months ago, now it's in Capricornus, you know, and so, yeah, it went there. But it did that across the sky. So if you try to pay attention really carefully where the planets are moving through the heavens, you don't get this perfect sphere that's going around in circles. You get little wiggly motions. This is the path of Venus from a few years ago through the heavens. Venus doesn't move just around the heavens on a perfect sphere, so something else must be going on. So people started to come up with new ideas that kind of preserved the notion of this quintessence, but they did it in a slightly different way. So here's the motion of Venus as tracked out from the point of view of Earth. This is a geocentric model of the motion of Venus, and it's actually a very precise geocentric model. You can actually see that Venus gets really close, and then it gets really far away. The sun goes around the Earth, and you know, Venus is not going around the sun, it's merely going around, the sun is going around the Earth in a nice circle, and Venus is going around the Earth in this weird little loop-de-loop thing. So people looked at this, and they actually figured, okay, well, it looks like Venus is actually doing some other sort of motion. So let's take a look. Here's a picture of Mars and Saturn. Another thing they noticed is that the different planets would do the loop-de-loop in a slightly different way. So Mars's loop-de-loop was pretty big, and Saturn's loop-de-loop was pretty small. You know, so some of the planets had very small loop-de-loops, some of them had really big loop-de-loops. And so you could actually make a graph of the way these loop-de-loops would actually work. So Mercury had a pretty big, simple loop-de-loop. Venus had this very complicated thing. You went out further and further, and Saturn had a very narrow set of loop-de-loops. And so another gentleman, a few hundred years after Aristotle came along, and decided that maybe Aristotle needed a little bit of tweaking. And he decided that the geocentric model, prima facie, obvious, you know, the Earth is still at the center of the universe, but the planets are traveling in these beautiful crystalline spheres, but they're not traveling directly on those crystalline spheres. They're traveling on these little whirligig things that are slightly offset from those crystalline spheres. Extra little loops. And so as these planets go around the Earth, I almost said the sun, they actually wobble a little bit in the sky. And that's what accounts for their loop-de-loop motion. And so this is the model of Claudius Ptolemy. You get this extra little loop-de-loop. Here's the whirligig. It's kind of like the spider ride at the fair from my youth. That extra little whirl gives it that loop-de-loop motion that we saw. And the loop-de-loops get smaller and smaller as you go from Mars to Jupiter to Saturn and so on. So here's the model of that. And there's just a lovely picture of Ptolemy using a quadrant. Now, Ptolemy had a bit of a benefit. He was one of the earliest people to actually take really good measurements of the positions of the planets. He mapped the sky really well. He had a star map which had slightly over 1,000 stars in it, and he took notes on the position of the planets relative to those stars. And so he was able to use this to develop his theory of the geocentric universe. So let's take a look at the way this actually works in practice. Here's a model of the Sun, Venus, and Earth. Now up here, you'll see the way, if they had hypothetically had a telescope back in those days, what Venus would look like. And we will learn that that is a deciding factor in deciding whether or not this model is actually particularly good. So let me play the So you get the loop-to-loop, and this is when it's on the morning side. This is when it's close to the Earth. This is when it's on the evening side. There we go. Now take a look at the position. We never actually see a full Venus. We're only ever seeing a half Venus because Venus is always on this side of the sun. The loop-to-loops can't cross one another, they thought. That would be bad. You know, that would somehow bring the whole edifice crashing down. So give me just a second. I want to leave the talk here. I was going to record my screen for the purposes of the video that I put online, and I forgot to do that, so I'm going to have to reconstruct it when I get home. But this will help me out. I apologize. I'll cut this out. Slideshow. Go back to slideshow. There we go. So that is the way they thought of the motion of the planet Venus. But here's the problem. If you were a good scientist or a good observer, so to speak, they didn't use the word scientist in those days, of the motion of the planets, you noticed that this loop-to-loop here and the model of the crystalline spheres didn't actually correspond precisely to the motion of the planets. The planets would drift from this loop-to-loop motion. So what they did was they decided, well, okay, maybe we need to make another little tweak. That tweak was to not put Earth at the very center of motion. The Earth was still fixed, but the center of motion was slightly offset to a point they called the eccentric. So if you were eccentric, that's what that means. And that did a much better job of predicting some of the drifting from this model of the universe. So it did a fairly good job of showing the position of the planets. You could count horoscopes and things like that and figure out where the planets would be in the future based on this. But here's the problem. We now know orbits are elliptical. And that model is not going to cut it. Because it's always, the more precise you get, the more you will realize that the movements will drift from the model. So here's what they did. They put extra epicycles on that. So they put epicycles on epicycles. Now here's the thing. The rule that they gave themselves was that all of these motions had to be perfectly circular. Why did they have to be perfectly circular? Because quintessence is perfect. It moves in perfect circles. What is the most perfect shape in the universe? The most perfect shape in the universe is a circle. Everything is the same distance from the center. It is a perfect shape. So these all had to be circles. Now you may think that it would be really difficult to get an elliptical orbit out of this way, and you would be correct. But it's not entirely crazy. They inadvertently discovered something that would be known to 18th and 19th century mathematics, which was known as a Fourier transform. So here's a model of the motion of the model of Venus per Arabic astronomer in the 14th century, and you can see it's getting rather complicated. We're adding epicycles on top of epicycles on top of epicycles here. A lot of the knowledge of Greek thought was preserved by the Middle Eastern empires through to about the 14th century, and that's actually what kept the Greek models of the universe. So these models, by the way, when you were one of these people, you probably were an astrologer. And as an astrologer, you didn't want to really give up your secrets very well. And so there are stories of epicycles on epicycles on epicycles and epicycles, and of people getting good models of the motion of the heavens by simply adding more of these epicycles to the mix. However, because you were an astrologer and you didn't want to give up your secrets, you tended not to publish your epicycular model of the universe. A lot of that stuff is lost. We just hear about it indirectly, and this is one of the few that actually kind of still exist. But enough of these were done to get a pretty good idea of how big the universe ought to be, and they went back to the size of the universe based on the guesstimates of Aristarchus, even though he was completely counted out in terms of the heliocentric model. He thought that he had a good grasp of the size of the universe, and I love this chart made in 1568 by a Portuguese, Bartholomew Velho, and he writes down the estimated distances to the various crystalline spheres, and I love how precise they are. I'll give you the firmament is 33,350,353.5. These guys really were precise. I don't know how they got so precise, but that's what they were doing. So they got a pretty good idea, or so they thought, of the scale of the universe. That was 33 million miles, at least, to the firmament. But the idea that you could create an ellipse out of these epicycles is not entirely crazy. You can, in fact, break down just about any shape using a mathematical technique known as a Fourier transform. You can actually take the wave form of all of these, and if you add enough of those circles, it sometimes takes thousands of them, you can make a pretty complicated shape. And so I want to show you a couple movies here that show you that you can, in fact, do this. So here is one model. Let me see. Oh, I think I'm at the end of there it is. Let's watch this. This is a rather complicated shape. It's a lovely musical note. Every one of these is uniform circular motion on top of uniform circular motion. Now, if you want to know how many there's several hundred of them in order to form this. So it's a pretty capable system. So indirectly, in order to try to save the system, they found a pretty good technique for developing the shape. If they had added just enough circles, they could have come up with something very close to an ellipse. Let me show you another one here. Hold on. Here's the other one. And I'm going to turn up the sound here. And I want you guys to tell me as soon as you figure out what it is. Okay, so this is a person determining that the system of epicycles is whether or not it's a good system. It's a long. So I want you guys to tell me what you think the model is. And I think this had something like 298 epicycles in it. It was a lot. Okay, we're going to follow it really well. Let's speed it up here a bit. Okay. And we will determine. Anybody got it yet? Now, this is not cheating. All of those are uniform circular motion. The arrows are going around in a perfect circle. And so, the guys that developed the model of the universe, the model of the solar system, using epicycles, were not crazy. They just didn't go far enough. They could have developed a model of the universe that got the orbits really, really close. They just had to add enough epicycles. So anyway, there you go. And I think it plays the Simpsons songs. Now, not everybody, I don't want you to think that the entire intellectual world in the Middle Ages was of one mind. There was a philosopher by the name of Averroes. He was a Moorish scholar living in Spain, and he had an Arabic name, and the reason why they called him Averroes is that that was his name. And Europeans are notoriously bad at pronouncing Arabic names, and so they called him Averroes. He thought that this was particularly ugly. He didn't like this adding epicycles on top of epicycles. It seemed like it was jury-rigged. He wanted something more pure and pristine, more in line with what Aristotle originally taught, which was these beautiful crystalline spheres. He thought that the loop-de-loop motion of the heavens was our fault, basically. It was our inability to appreciate what was going on. There was something ineffable up there that we could not understand. So Averroes lived at a time when these medieval schools were going through a process of interrogating the world in a very different way than the way we do it today. When we try to figure something out about the universe, we build a Large Hadron Collider and we fire atoms at each other and look what comes out and interrogate the universe directly, physically. We actually look up at the universe in order to see what it's all about. We see what's going on up there by taking really accurate measurements of the spectra of light of the sky and everything like that. They had a different way of doing things. And the main technique in the universities in those days was something called disputation. And here's an illustration from that time of disputation. Disputation was primarily a technique for settling religious arguments, which was basically every argument was a religious argument in those days. Your model of the universe was highly based on your religious argument, and it was generally, and I'm very sorry to say, a way for Christian scholars to kind of diss Jewish scholars. Basically it was a way to say, we're right, you're wrong. But it was the technique of interrogating the universe. So the way disputation worked is it was basically a debating technique, and it's a fairly interesting debating technique. It was taught to university students and monastic scholars, and it had certain things that it did. Certain ways that they thought of the universe when they did a disputation. For example, if things looked alike, then they ought to be alike. For example, if you find a little root that looks like a heart, well, that root must have something to do with the heart, so maybe it's good for your heart, so we'll eat it, to see if it's good for the heart. If you have something that looks like a bone, well, maybe it's good for the bones or something like that. They used the model of similarity in order to determine whether or not something was true. And the other thing they believed was you couldn't trust the human senses. Think about it. In those days, we didn't have telescopes, we didn't have microscopes, we didn't have Large Hadron Colliders. The universe was hard to gauge with the naked human eye. We couldn't actually understand it particularly well. We weren't good at measuring angles. How many people can hold up 10 degrees exactly? Yeah, sort of, So you can't trust human senses. We're not particularly good. Optical illusions are something that they were really into. And the material world around us is messy. And it's not the truth, meaning what we see is not really the essence of the way things are. And experiments are less valuable and trustworthy than logic. So this guy right here influenced these last two. Plato, if you've ever heard the story of the cave, the parable of the cave, the idea that Plato had about the universe was that he wanted you to imagine a person that was in a cave tied to a rock, and all he could see was the shadow of people walking by outside, the forms of the universe. He could only see the indirect shadows of the people. So Plato said, our view of the universe was like that guy in the cave seeing those shadows. He wasn't seeing what was really out there. His senses was providing us with a bad impression of the way the universe really worked, a limited impression of the way the universe worked. And he had a technique of debating which convinced him that logic, debating things, was a much better way of getting at the truth than actually doing experiments. So disputation. Let's take a medieval disputation and interrogate the universe in an interesting way. this is an extremely simplified version, and this represents no particular one. But so the first thing you would do is you would state the proposition. You would get up there and say, does the Earth move? I think not. You know, so you would the courtesy that you would do is you would actually present the objections first. You would actually say, this is the way this other people would think. Usually there wasn't anybody on the other side. This was something you did in writing. Usually, you would say that it seems the loop-to-loop motion of the planets could be better explained if the Earth were to go around the sun rather than vice versa. The sun appears bigger than the Earth, as it is clear from lunar eclipses, and it doesn't make sense that something so big would go around something so small. Now, here's the deal. They presented an argument. I say the Earth does not move. Have you ever seen something that you've been in that you cannot feel when it's moving? The lunar eclipse model is worthless because our corrupted eyes here on the corrupted Earth can't understand what is really going on. Plato taught us that. The loop-de-loop can be explained just as well by Ptolemy's model of the universe with the epicycles. And, very important, it is over 1,000 years old at this time. The Ptolemaic model has been around for a really long time. So who are we to question? This thing has survived 1,000 years. You know, it would take a lot of hubris to overthrow that. The most important element of this, and I accidentally skipped over it here, was the most important element of disputation was the text. Something that was written down was everything. And in particular, something that was written down by one of the great authorities of the past. So you appeal to authority, so they get out the Bible and they say here on Psalm 105 it is written, he set the earth on its foundations so that it should never be moved. And Aristotle agrees with this, so I win. You know. And then you would reply to it, repeat, and everything like that. And by this method, you would actually refine your view of the universe. Now, in our modern sense, this basically just kind of reinforces what you already know. You know, if you have an authority that tells you something and you want to figure something out, you probably want to try to disprove it. But they considered this to be a really good method of actually understanding the universe. One interesting element of this, since it was usually a solitary pastime, was that they would spend an awful lot of time attempting to get rid of contradictions in text. So if something in Aristotle disagreed with something in the Bible, they would put the two of them head to head and try to resolve the contradictions. This was called saving appearances. Now, what was the biggest authority in those days? What was the authority that they called upon the most? The church. Exactly. So the church was, at least in Europe, was the biggest authority of them all. It had a higher influence, and the authority that they most often appealed to, and what shows up in disputations all the time, were biblical passages. They very often would find biblical passages. So here's a few that I found that describe the earth as being relatively motionless. My hand laid the foundation of the earth. That basically means the earth is solid. These are parts of the Bible that seem to suggest that the earth does not move. And yay, Aristotle also said it, so it must be right, right? Okay, so, and then I found a website that actually found all of them, and there's something like several dozen. So these are several dozen biblical passages. You can't read them at the moment, but just to show you that there's a lot of biblical evidence to suggest that the earth is at the center of the universe. So they had it on good authority in those days. And once again, they indulged in this practice of attempting to save appearances when there were contradictions. Most of the writing that survives from ancient disputations were taking two passages and attempting to reconcile them. This was called saving appearances. And it was a really good way of making sure that the whole system stayed in order. And it created some weird ideas about the universe. So, and by the way, that scene in Monty Python where they weigh the duck, That's a really good example of medieval disputation. It's a little exaggerated, but that's actually that's a very accurate portrayal of medieval disputation. So getting back to Aristotle, here's our model of the universe according to the Middle Ages. The material cause, quintessence, crystalline spheres. That's what causes. The formal cause is the prime mover, whoever that may be. The final cause is God's plan, whatever ineffable plan that is. And the efficient cause is God. Well, God seems to answer everything, so we're done. And some of the interesting ideas that they had, this transferred over into other sciences. This is a model of the universe based on the four humors, which were mirrored onto the four elements. So you had caloric. It was thought that the human being was balanced if these four humors were balanced in the body. Caloric, phlegm, blood, and black bile. If those were all in alignment, then everything was good. If things were out of whack, then one of them was lacking or something like that. So if you had too much blood in you, for example, they would bleed you. If you were choleric, you would cough out the whatever it was that you needed to cough out and that kind of thing. So that was their model of the universe. And this was actually, in the writings, these were actually mapped onto the elements. And then the fifth element, the quintessence, was your soul. You had a spiritual element, and that was the fifth final thing that brought it all together. So this was a pretty sophisticated model of the universe. And if you wanted to overthrow it, you had to get through this tangle of, this web of associations that they had built up for 1,500 years at least, a really long period of time. And it was extremely influential. We've all heard the story of how Johannes Kepler worked so hard to develop the model of the universe based on ellipses rather than perfect circles. But his first attempt at developing a model of the universe was attempting to use those 5 perfect solids to figure out the distances to the planets. He thought that, hey, if I nest them one inside of another, I will get a good model of the actual distances out to the planets. And he failed because it doesn't have anything to do with it. But even Johannes Kepler in the 1600s, 1900 years after Aristotle, was still trying to figure this out. So we get to the Middle Ages. We leave the Middle Ages, and we get into the early Renaissance. And so I will have to change my shirt. So here we go. There we go. So we get into the Middle Ages with Nicholas Copernicus here. Let me readjust my microphone. Maybe. So Nicholas Copernicus thought, okay, this particular model of the universe is preposterous. This whole epicycles thing is far too complicated. Let's just get back to basics, put the sun at the center of the solar system, and everything will make sense. But the problem was, it didn't convince a lot of people. And in fact, the church was really against it. And they made him basically put a disclaimer in the original publication. He basically said, this is just a nice, convenient mathematical model that saves the appearances of the sky. It actually makes the sky work really well, but we don't really think that the universe works this way. So Copernicus, it was supposedly revolutionary, but it didn't have, a lot of people did read it and thought about it, but it didn't really change the way people taught things. And one of the reasons why it didn't change the way people thought things is another thing that the geocentric model of the universe has going for it. And that is the lack, or apparent lack, of parallax in the sky. Parallax is the motion of things from side to side when you yourself walk from side to side. So if I'm looking at Isaac here, Isaac will move over there, And then if I come over here, Isaac will move over here. People thought that that sphere of stars was a literal sphere of stars. And they had a rough idea of how far away it was, 33 million miles or so, something like that. So if that were the case, and the Earth was going around the sun, you would actually see the stars over here getting a little bit closer on this side in June. And then back over here, you'd see these stars over here getting closer in December. Because you could not visually see that, and Tycho Brahe, the astronomer who was the greatest measurer of the sky in the pre-telescopic era, couldn't determine parallax. And so he didn't believe in the geocentric model. He had a slightly hybrid model. He didn't believe in the heliocentric model. He believed in the geocentric model. But the lack of parallax was a really good indication that the geocentric model, the model around the Earth, was correct. But then there's this guy. And this guy did something pretty spectacular. But before we get to that, let's take another journey to our third object. And I apologize. I promise you that that was the longest part of the talk. We're about 2/3 of the way done here. The third object is an indistinct little star, just a bit brighter than, just a little bit dimmer than 5th magnitude. You can see it with the naked eye. Probably on a good clear night here at Perkins, you could see it. That star is 61 Cygni. Now, I'm not going to tell you why I picked this star just yet, but I want to talk to you a little bit about stars in general. Let's go back to Ptolemy. Ptolemy, as you remember, made a map of the sky. And in so doing, he did something kind of interesting. He paid attention to the brightness of the stars, not only the position, but the brightness. And he divided the stars into categories depending on how bright they were. So he put the brightest stars in a box, and he called that the stars of 1st magnitude. The second brightest stars in a box called 2nd magnitude, and so on, down to 6th magnitude. And that lives on today in our backwards magnitude system, where dim stars are in fact given higher numbers in the magnitude system. So a 15th magnitude star is about the dimmest thing that your 8-inch telescope can see. A negative 27 magnitude star is the sun. So it's inverse. That is why we see things that way. It's because of Ptolemy. So Ptolemy's program, map of the universe, was called the Almagest. That is the Arabic name. It starts with AL. It was translated and passed on to us through the Arabs. And here's a picture of the Greek translation of Ptolemy. You can actually see this is the constellation. This is where the stars are in a figure. He usually gave them a longitude, latitude type position, but he also gave a description of where they were in the figure. So if it was Leo, he'd say this is the head of Leo or something like that. So this is just what it looked like. That's just what Ptolemy's manuscript would have looked like. Other people were also doing this at the same time. I don't want to discount them. I apologize, it's mainly a European journey, but other people were doing the same thing in China, for example, and in the Middle East, who inherited a lot of the Greek knowledge. This Ptolemy's model was improved upon by an Arab astronomer in the 10th century by the name of al-Sufi, and he will show up here pretty soon. And I present al-Sufi because he actually made the map of the sky a lot greater. He included about 2,600 stars, of which 61 Cygni is one of those stars. And he measured the positions very, very carefully. I just wanted to show you a few of the pictures in his map of the sky, and I wanted you to kind of guess what these are. That's Orion. Which one's that? That one's Aquila the eagle. That one, this one's probably pretty easy if you focus on this guy right here. This is Perseus. Perseus, and this is where Algol is. This is the Medusa star, Algol. So the constellations in the Arabic world were very much the same as the constellations that the Greeks had and that were passed on to us. And so Algol, the ghoul, is the star on the eye of this monster right here. And Al indicates that it came from Arabic. It just means the ghoul. Al means the. This one, that's a little harder. That's a Riga, the charioteer. Here's his whip, okay? And one very important thing that will come up a little in just a short while is that Al-Sufi measured the positions and the timings of events related to the moon. He liked it when the moon would pass in front of Mars, for example, or the moon would pass in front of a bright star. And in particular, he took ancient records and compiled them. And one ancient record that he had in his list was a particular occultation of the star Aldebaran that occurred in the year 509, as seen from Athens, Greece. Now, this is a long time before he was around. Oh, that's there. So we get to the age of the telescope. Yay, everything changes. And we get a new view of the universe based on Galileo's observations, which throw a big wrench into some of these models of the universe. So let's take a look at what he saw. We'll go back to the planet Venus and take a look at the way planet Venus, this is the symbol for Venus, by the way, go back to the planet Venus and take a look at how it looked through the telescope, and you'll notice that when Venus is really far away, it was actually nearly a circle. Now let's go back to this model here and watch the way things ought to look. Hello, come on. Well, that won't happen. Wait a minute, there we go. That won't happen in the geocentric model, because Venus will always be between the sun and the earth. You'll never see a full Venus over on the other side of this, or a nearly full Venus over on the other side of the sun. So Galileo threw a wrench into the geocentric model of the universe. Another thing he did was he took really copious notes of other worlds. Do you guys know what that one is? Jupiter, exactly. So the idea of quintessence was that uniform, perfect circular motion was centered on the Earth. Those epicycles, let's just forget about that. They kind of ignored that. But the idea was that the motion was centered on the Earth. Well, Galileo, taking very copious notes, figured out that not all the motion was at the center of the universe, was at the Earth. There was actually some motion around Jupiter. You had things going around Jupiter, these little moons, so to speak, going around Jupiter itself. And so that also threw a wrench into the system. And what really benefited it was he wrote it down and he published it. He shared it with the world, which was something that was rather uncommon. He wanted to tell the world about it. Remember, kids, the difference between science and screwing around is writing it down. So he also looked at the moon, realized the moon was not perfect and everything like that. That's something I hadn't talked about, but he drew these lovely images as well. So this model, with the sun at the center, is starting to phase out this model, and the universe is starting to grow. We're getting a new view of the universe. Here's Earth right here with the moon going around it. This is much closer to the actual model of the universe. Well, if this is the case, that the Earth is actually going around the sun, then that firmament out there, that sphere of stars, has to be awfully far away for us to not have seen the parallax. Well, how far away was it? And how would we figure out how to deduce how far away the universe was? So, that's no longer part of it. So some of it actually helped out that Johannes Kepler devised his 3 laws of planetary motion, and that gave us a quantitative sense of how far things ought to be. He got a good indication of how far away the planets ought to be from the sun based on the timings of their orbit and his 3rd law and that kind of thing. So we got a good impression of the relationship between the orbits. We didn't know precisely how far away Earth was from the sun, the Earth was from the moon, and that kind of thing. But we had a good idea of how many AU Jupiter ought to be from the sun, for example. How many times the distance between Earth and the sun, Jupiter and Saturn and Mars ought to be from the sun. So if we could figure out how far away the Earth was from the sun, we could figure out the scale of the solar system and get a good, precise measurement of the size of our little nook of the universe. So here's the actual scale. It's kind of hard to see here. This is just from a program that I got to show you how far away it is. And we've got Mercury, Venus, Earth, Mars, Jupiter, and Saturn right there. So that gives you a rough idea of the scale there. So, was the universe really big and looked a certain way, or really small and looked a certain way? So we needed to kind of figure that out. So it started, the story of how we figured out the scale of the solar system started with this thing called the Rudolphine tables, of which Johannes Kepler played a role, and he published them in 1627. This was a prediction of the positions of the planets based on the observations of Tycho Brahe and a number of other ones over a really long period of time. And he was able to predict where the planets would be in the future. And not long after, people realized that every once in a while, the planets would pass in front of, at least Mercury and Venus, would pass in front of the sun. And we would be able to use that in order to deduce the scale of the universe. Now, people didn't figure this out right away. And there was one transit of Venus in 1639 that was observed by these 2 English gentlemen, and they were total amateurs. They were the first people ever to observe a transit of Venus, and they did it roughly in the same way. This is Jeremiah Horrocks, and this is William Crabtree. And if you'll see, they both died pretty young, which is kind of a thing in those days. A lot of scientists live a really long time, but these guys didn't. So anyway, they observed it, and this was a drawing based on a verbal description of the event that was made. Now, they hadn't at that time figured out how big it was, but along comes this guy, Edmund Halley, and in right around the turn of the 18th century, published a dissertation, Parallax of the Sun by the Transit of Venus. He figured out that if you could time the movement of Venus across the face of the sun from one position on the Earth and time it from a very different position on the Earth where Venus would actually appear a little bit higher or a little bit lower in the sky, you would actually be able to figure out how far away the sun was. And it was a pretty clever technique. The problem is the transits of Venus are really far apart. They're 112 years apart. Now, the good news is that there's 2 of them really close together. So here's the technique. If you happen to be, up here in, Europe, you would see Venus cross over here. And if you were in Africa, this is exaggerated a little bit, you would see Venus cross down here. Actually, it's the other way around. You would see, in Africa, you'd see it here, and in Europe, you'd see it here. And if you were far enough apart, the difference between those 2 would give you a good estimate of how much Venus had moved up and down. Now, it can't happen that Venus is moving right across the center because the timings would be exactly the same. It's best when you get a real edge-on kind of transit. And luckily, most of the transits are like that. So they would have two opportunities, he predicted, in 1761 and 1769. Now take a look. The last one was in 1639. See, they had to wait a really long time for this to happen again. They tried with the planet Mercury, but Mercury is too small, and they didn't get good results. Mercury passes in front of the sun more often. And so the first opportunity was observed by just a few people. This is one this is a gentleman, and it's on the list. It's Monsieur Impey, which is his name, Y-P-E-Y. He was French. But there was a problem right here. At the time, there was a war between France and England. They called it the 7 Years' War, which tended to make travel by sea a bit perilous. And you didn't want to go on a scientific journey because you would probably get your boat sunk and you would die. And so not a lot of people traveled the world in order to get the other parallax motion. So the first one, after over 100 years, was lost. But the second one, they'd wrapped things up. The war was over. French and English were back on speaking terms, or at least the scientists were. And so a number of people across the world decided to give this another go. And one of them, the person that was going to travel the furthest to get the parallax measurement from a long distance away, was this gentleman by the name of James Cook, who traveled around the world. And he himself, even though he was the captain of the boat, actually made the measurements. This is his observatory in a tent. He went to Tahiti, kind of nice. He complained about the bugs. He had a bit of an issue with the timing here. The problem with Venus, or the problem with looking through a telescope, is there's some weird optical illusions having to do with the seeing, and you end up with these weird effects. So it's real hard to tell. Is that Venus hitting the edge of the sun, or is that Venus hitting the edge of the sun? It was hard to know. But he did a good job and guesstimated, and they ended up getting a bunch of good measurements of the transit time of Venus. Here's a map of a bunch of them going across the face of the sun, as well as the timings. And they guesstimated, they nailed down 1 AU to roughly 95 million miles. The distance from the sun to the Earth was 95 million miles. Now, that's pretty good. The modern value is about 93 million miles. So that's really, really good in hard conditions, just by eyeballing the planet Venus through a telescope. So now we've got a good measurement of the scale of the universe. We know how big the planets are, the orbits of the planets are relative to one another, and we know we've got a datum point for how big the Earth-Sun distance is. We've got the scale of the universe. And here's the problem. We still don't have parallax. We can't see the motion of the stars. The stars don't wobble from side to side. Well, let's go back to Aldebaran here. This is in the Hyades. And back to that observation that was noted by Al-Sufi in the year 509. And a gentleman by the name of John Flamsteed was paying very careful attention to these records, and he was laying down his famous map of the night sky, and he put Aldebaran on his map, which found its way to the desk of, let me see here, I'm trying to take a look here. Oh, I don't have that slide. I'm sorry. Anyway, John Flamsteed took measurements of the stars and the brightness of the stars, created a map of the positions of all of the stars. His collection of his atlas was basically just a list of the longitude, or the right ascension and declination of all the stars in the sky. He didn't make a lot of maps. He gave the stars, the brightest stars, their modern names, but he also gave some of the dimmer stars numbers based on their position in the constellations. One of the stars that he named was 61 Cygni. It was the 61st star that didn't have a name as you went from east to west across the constellation of Cygnus. I'm going to skip ahead a little bit here. This gentleman here figured out that you could probably deduce which stars might show parallax by figuring out how fast they appeared to move across the sky. The slide that I was missing was a picture of Halley. Halley actually took that measurement from the 509 occultation of Aldebaran and figured out that in his day and age, that would not be possible. Aldebaran, this star in the Hyades here, had to have moved since 509, 1,300 years later. It had to have drifted probably about 7 arc minutes. That's about a fifth the width of the moon. But he figured out that it would have had to have moved. And this is the first indication that the stars are not fixed in space. And that gave this gentleman an idea. He said, hey, if you look at the stars in space, let's assume that all the stars are moving every which way. The ones that are the closest will actually appear to be moving the fastest. And the ones that are the furthest away will actually appear to be moving much slower. So, if you're looking out a car window and you're looking at the things that are nearby you, they'll be moving much faster. They're blurred in the camera view here. But the hills and the trees in the background appear to go much slower. They'll look sharp in the camera view. So just like that, the stars that are nearby would be really good candidates for trying to find parallax. So this comes to one particular star, 61 Cygni, that has a very high motion across the sky. By the way, they call this motion proper motion. And here's a map of the position of 61 Cygni. And if you look at the little star next to it, you can actually see that it's moving. This is about once a year. And you can actually see it's booking along here pretty well. It's booking along pretty well. So 61 Cygni was a good candidate. So let's see how, here's putting all those images together, and you can watch 61 Cygni move 1 frame per year. So that gives you a good indication that it's relatively nearby. Now there are closer stars than that, and there was one in particular that is in the southern hemisphere called Alpha Centauri, naked eye star, that was a very good candidate because it has very high proper motion. It's moving across the sky particularly quickly, and people attempted to make an observation of it. Now it's really hard to make an observation of the position of the stars in the night sky. Here's the instrument that they would use to do it. This is called a heliometer. And the way you did it was you put the star in question on the bottom half of the field of view. And then the lens at the optics was split. And one half of the field of view would captured a background star, another star, and one half of the field of view captured the near star. And you turn this little knob on the side of the telescope, and it brought the two of them together. And how much you turn the little knob indicates how far apart they were. And you measured the distance between two stars in the sky, presumably the one that's really close by that moves a lot, and the one that's really far away that doesn't move quite so much. And in so doing, you could measure the parallax of this. Now we're dealing with very small amounts. Let's take a look at how small of an amount there is. 1 AU, we remember, is 93 million miles, 95 in those days. And the distance, if you took a motion of the star 1 arc second in size across the sky, that would put a star 3.26 light years away. 1 arc second of motion in the sky, one little wobble of 1 arc second. Well, just to give you an indication, this is a picture of the planet Neptune. At its biggest, the planet Neptune is 2.4 arcseconds in size. It's a tiny little world. So we're dealing with something that's less than half the width of Neptune in the sky. So it's really tough to measure parallax. To top it off, stars don't appear as single little points of light. This is a picture of Sirius taken through a telescope here. Sirius spreads out. The light in the optics glares. It glares in your eye. It glares in the atmosphere. So we're dealing with a blob that is probably roughly the amount of size in the sky as the wobble. To top it all off, it's moving. It's moving from place to place, so you have to cancel out the motion. This gentleman was living in South Africa at the time, and he made what appears to be the first measurement of parallax of what turns out to be one of the nearest stars, Alpha Centauri. The problem is, he measured the parallax of Alpha Centauri to about 1 arcsecond, which would put it about 3-ish light years away. We know now that Alpha Centauri is about 4 light years away, so it's a pretty good measurement, pretty good for the time. He did it in 1837. Here's the problem. He wasn't really comfortable with the fact that his measurements were accurate. His heliometer wasn't that good. And so he didn't feel like he could publish. He didn't want to embarrass himself. So he didn't publish. And so we don't remember his name. He's lost to history. But he made what was probably the first relatively accurate parallactic measurement. So this gentleman by the name of Fraunhofer made a much better heliometer. And it was picked up by this gentleman by the name of Friedrich Wilhelm Bessel. And it just goes to show you that when you have better instrumentation, sometimes you make most of the time you make better discoveries. Sometimes the person who makes the discovery is the person who has the best telescope. Remember that. So he decided that he would take one of the stars with the highest proper motion and measure it. He measured 61 Cygni. Now here's the problem. You'll notice that 61 Cygni is a double star like the sun of Tatooine, and he had to cancel out the motion of the two stars around each other. Fortunately, the orbital period was guesstimated in those days to be around 400 years, so it wasn't particularly difficult. But you had to actually cancel that out a little bit to get an accurate measurement. So he plotted the position of 61 Cygni in the sky, figured out how much to erase, and then went from there. And he got a measurement to 61 Cygni of 360 milliarcseconds. A milliarcsecond is 1,000th of an arcsecond, so this is 0.36 arcseconds. That's 1/3 of an arcsecond. That's like 1/8 of the diameter of Neptune. That's a tiny little measurement, but he got a relatively good and relatively precise distance to 61 Cygni, and to top it off, he published. And so we remember his name as finally figuring out once and for all how far the stars were, or at least the closest ones. So here's his figures, 360 milliarcseconds if you figure out based on 1 parsec. How far that is, that makes it about 10.4 light years away. The modern value is about 11.36 light years. That's a pretty good figure for those days. I mean, just using an 8-inch telescope with a refractor and a little split lens and doing 2 measurements on presumably not great nights 6 months apart, that's a pretty extraordinary measurement for 1838. So let's go back to the final object, and this is the end of the line here, to taking the universe from 18 times the size of the Earth moon distance to pretty darn big, that 133 million, to the size of the distance of the stars to as big as we know it today. And let's go back to Al-Sufi's maps here. and get our first indication of this particular object. Here is our last object, M31, the Andromeda Galaxy. Now, M31 didn't really stand out to people in the history of astronomy. Not many people mentioned it. Doesn't appear anywhere in classical writings. There it is right there. And if you've ever been out under the sky, I know where it is. It's right there, but it doesn't draw the eye. You do have to kind of look at it, maybe use a little averted vision to see it well, and that kind of thing. It doesn't draw you in. So people didn't take note of it for a really long time. However, Al-Sufi did take note of it. He called it the mouth of the little fish. And this is the little fish in Andromeda. This is just his drawing, and this was his rendition of M31. First mention of it in history was Al-Sufi. So he did a lot. First telescopic mention doesn't appear in any writings between the time of Al-Sufi and this gentleman, an English astronomer by the name of Simon Marius, and he was the first person to observe it through a telescope. He actually did it about 1 year after Galileo made his observations. This was Simon Marius, 1612, 2 years after Galileo made his first publication. So this is not a drawing by Simon Marius. This is actually a drawing by Charles Messier, but he's crediting the discovery of this nebula, which he called, to Simon Marius. He didn't even know about the other observation of Al-Sufi. That's how little people paid attention to it. Simon Marius was given credit, even though he was about 600 years too late. So people started observing the night sky through better and better telescopes through the 17th and 18th century. And they started to notice that there, as we do as amateur astronomers, that there's a lot of faint fuzzies out there. And they started to see that the faint fuzzies were in different forms. There are, some blobby ones, some little oval-shaped ones, and that kind of thing. And as people tend to do, they tended to hypothesize about what they were. And one early, pretty prescient guess was made by this gentleman, Immanuel Kant, who I will recommend not reading. He is extremely tedious. But just to give you an indication, this is how he says, I think that these are other Milky Way galaxies. It is far more natural and conceivable to regard them as being not such enormous single stars, but as systems of many whose distance presents them in the narrow space of light, which is individually imperceptible from each of them, reaches us on account of their immense magnitude and form of a pale glitter. Their analogy in the stellar system, which we find ourselves, their shape, which is just what they ought to be. According to our theory, the feebleness of their light, which demands a presupposed infinite distance, all of this in perfect harmony with the view that these elliptical figures are just universes and, so to speak, Milky Ways, like those whose constitution we have just unfolded. Got that? That's how Immanuel Kant reads, by the way. I just wanted to present to you a warning in case you decide to read the universal natural history and theory of the heavens. To boil it all down, Immanuel Kant thought that these little fuzzy oval things were other Milky Ways out there. How did he know that? He just kind of guessed at it. They just kind of look like it to him. So people tried to get a handle on the Milky Way itself, our Milky Way, our galaxy. One of the first gentlemen to try to do this was an astronomer by the name of William Herschel, discovery of Uranus, which he called George. That was his first name. That was his suggestion for the planet Uranus after the king. Of course, he did it in Latin. But this right here is his map of the Milky Way. The sun is at the center. And he decided that he would figure out the size of the Milky Way by looking out and counting the number of stars of different brightnesses that he could see through his big telescope. And he gave a pretty good map. Now, this here is kind of a place where there's lots of gas and dust, and he didn't think it was gas and dust between the stars. He just thought it was a place where there were fewer stars. And so he gave a pretty good view of the fact that the Milky Way is somewhat flat and it spreads out in all directions. That's a moderately good map of the Milky Way. I got a better telescope. This is a 48-inch scope, largest telescope of its time, and started to make drawings of these blobs and that kind of thing, and that started to give people ideas. This was the scientific age. People wanted to figure out how the universe came into being, and one of the things they wanted to know was how stars formed, how our solar system formed. And they developed something called the nebular hypothesis, which is actually pretty much the way we think star systems and solar systems form to this day. Basically, it's a giant cloud of gas and dust, swirls around, the center condenses into the star, and the outer portions of the cloud condense into the planets. It's a good model. And that's what they thought was going on with these. And in fact, William Herschel disagreed with Immanuel Kant. He said, these things must be star systems forming. Moving on a little bit further, we had one of the most independently wealthy amateur astronomers in history, William Parsons III, Earl of Rosse, in the middle of the Irish potato famine, decided to spend all his money not on his starving workers, but put them to work constructing a telescope. Now, suffice to say, he actually did house a lot of people and did some good. He got a bad rap for that. But he did spend a lot of money on this telescope. It was called the Leviathan, and it had a mere 72 inches across at the time. And this gave him, with the awful reflective quality of speculum metal, which is really bad, the ability for the first time to start to see that these little disc shapes that they saw, in fact, had some structure to them. What's that one? Do you know? Whirlpool Galaxy, yes, M51, and that was the first one, probably the easiest one to see the spiral structure in. This was in 1845. Now that, if anything, to them, looked like the nebular hypothesis in action. They thought, a lot of people thought, that this was a new star system forming. So, the thought at this time was that all of the universe was the Milky Way around us. The star system was the Milky Way around us, and that these other things, these blobs of light out there, were new star systems forming. They had it on good authority. Now, there's a bit of a problem, and I'll turn off the light here so you can see it a little better. There's a bit of a problem, and if you read my article in the Prime Focus this month, you will know about this. That if you map the location of all these little spirals here, and each one of the red dots is one of the spirals that is in the New General Catalog, or one of the blobs that is in the New General Catalog, you find that most of them are not along the plane of the Milky Way. Well, what's that all about? We got a bit of a problem. These things have to know where the Milky Way is. It can't be, they can't just, if they're scattered around the Milky Way, you'd think that there would be some in the plane of the Milky Way itself. You'd think that we would see them. So there's a bit of a problem here. And there was another bit of a problem, getting back to our fourth object. We looked at Andromeda, and we saw what appeared to be a nova in Andromeda. Now, for a couple hundred years, people had been seeing stars pop off in the night sky. Every once in a while, you get a new star. Nova means new star. Nova. Well, they saw a nova, or what they thought was a nova, in the cloud, the nebula that was Andromeda. Well, how does that happen? If this thing is nearby to us, it must be, is that? There we go. Yeah, that's good. It must be part of that cloud. How does a new forming star get a nova in it? And finally, people started to take photographs of these things. Up until this time, everything was by the eye. You had to make drawings. You had to use your flawed human vision. But when you could take photographs, this is in fact the first photograph ever taken of the Andromeda Nebula, at that time as it was known. And they looked at it, and it still kind of maybe sort of looks like, that model of star formation, the nebular hypothesis. So people, didn't really buy into the idea. A lot of people didn't really buy into the idea that these were extragalactic objects. But there were some issues here. People had taken spectra of the Andromeda Nebula and actually determined that it didn't look like a nebula. It didn't look like Messier 8, which has spectral lines in it. By this time, they knew about that. It looked more like it was made up of a bunch of stars. And when we look at this, we cannot see individual stars. So if it's made up of a bunch of stars, where are the stars? We can't see them. So there's some serious issues here with the problem. So that brings us to 1920s, and I'm going to do this in the form of a boxing announcer. Ladies and gentlemen, the great debate between Harlow Pomage Shapley and Heber Specs Curtis. Heber Specs Curtis was slightly older. Harlow Shapley was a young, up-and-coming upstart who wanted to prove his mettle. They got together and decided that they would debate once and for all whether or not these spiral nebula outside the Milky Way galaxy were in fact part of our Milky Way galaxy or outside of it. They did this on the 26th of April, 1920. At stake, how big is the universe? So here were the arguments that they had. So Harlow Shapley suggested that the sun was not at the center of the Milky Way. And he did so by actually mapping out the positions of the globular clusters in the night sky. And he saw that most of them were clustered around Sagittarius-Scorpius region. They were over there, not over here. There weren't many behind us. They were all over here, which seemed to suggest that we were not at the center of the Milky Way galaxy. Heber Curtis, on the other hand, thought that this was kind of preposterous. He disagreed. He thought the sun was near the center of the Milky Way. Harlow Shapley, is it going? Okay. Yes, good. Harlow Shapley thought that the Milky Way was extremely big, 320,000 light years across. As we know, the Milky Way is somewhere between 100 and 200,000 light years across, depending on how you measure the edge. But to him, it was 100 kiloparsecs across. That is extremely large. And Heber Curtis, on the other hand, thought the Milky Way was kind of small, 30,000 light years across. He thought Harlow Shapley looked at the spectra, saw that they looked like stars, but still thought that they were hot gas. And he thought it was just a warm, very, very warm gas that was not actually glowing like hydrogen-2 gas glows in the Orion Nebula or in the Lagoon Nebula and that kind of thing. He just thought that they were warm, hot dust and gas. But Heber Curtis said, no, spectroscopy shows that the spiral nebula are almost undoubtedly specular. So they disagreed on the interpretation of the spectroscopic data. And Harlow Shapley had kind of an ace up his sleeve. He had a friend by the name of Van Manen who had actually observed a spiral nebula and claimed that he had seen it spinning over a few years. He had actually seen the motion of the spiral nebula. He had taken a number of observations over a long period of time and came to that conclusion. Now, you cannot see the motion of a galaxy in the human lifetime. So if the galaxies were impossibly far away, that spinning would not be visible. So this was one point in favor of Harlow Shapley. Heber Curtis's response to that was, yeah, maybe, And so if that's, he actually said, yes, if that is the case, then my whole idea about this, about the fact that the universe is big goes down the drain. He said, hey, if you're right, then I lose, but I don't believe you. And then Heber Curtis said, you could see dust lanes in photos of the spiral nebula just like our Milky Way. He said, hey, look, the Andromeda Galaxy's got these dust lanes, so do we. It's like the Milky Way, right? And Harlow Shapley said, yeah, well, maybe that's an illusion. Maybe these nebulas forming new star systems had dust lanes of their own on a much smaller scale, and that's what we were seeing. So, in sum, Harlow Shapley, young upstart, thought that the Milky Way was more or less the whole universe. The Milky Way was really big, but it was more or less the whole universe. And Heber Curtis said, no. These are countless other galaxies. What was the result? The result at the time was that no one could make up their mind. It was a draw in the papers and the stuff that people wrote about it. They both made good arguments. In retrospect, we'll go over who was actually right. But in retrospect, it seems almost easy what the answer was. But at the time, people couldn't decide because there wasn't enough evidence to decide between them. So the actual consequence of this debate was that it was a draw. So back up a few years, and we have Henrietta Swan Leavitt, who was one of the Harvard calculators, and she determined what was called the period luminosity relationship. She actually took photographs of the Large Magellanic Cloud and found evidence that there was a certain type of variable star in them known as a Cepheid variable. They called them Cepheid variables because the most well-known and one of the brightest ones of them is in the constellation of Cepheus. And the way that you know a Cepheid variable from another type of variable star is just the pattern of brightness is a very distinctive sawtooth pattern. And she actually looked at a bunch of these Cepheids. Unfortunately, they're very bright and can be seen very far away. And she determined that these distant Cepheid variables, all presumably in the same blob of stars, the ones that had very high magnitude seemed to fluctuate much more rapidly, and the ones that had very low magnitude seemed to fluctuate a lot more slowly. By the way, this is the Large Magellanic Cloud here, which could be seen from the southern hemisphere. And so she figured out that there was a good way to determine the distance of something. If you could find a Cepheid variable in a collection of stars or in a distant system, you could actually measure its distance by figuring it, you'd know how bright it was intrinsically, because you know how bright Cepheid variables are, and you can tell it's a Cepheid variable because it had that distinct sawtooth pattern. So with that in mind, we get these two gentlemen, Edwin Hubble, pipe smoker. A funny story about Edwin Hubble is that he was from Chicago, Illinois. That's not the funny part. But he got a Rhodes Scholarship and went to England for 6 months, and he came back with an English accent, which he kept for the rest of his life. He affected a tweed jacket and a pipe for the rest of his life. He became an Englishman, basically. And his protege, a gentleman by the name of Milton Humason, who was also an interesting character. Basically, he dropped out of the 8th grade. He became a mule skinner. He was a mechanic and that sort of thing. He was basically just kind of a hands-on guy and got involved with the construction of the Mount Wilson 100-inch telescope on top of Mount Wilson near Los Angeles, which at that time was actually not very light polluted, and got so good at, in fact, hanging around and cleaning up the place, he was eventually invited to start making observations on his own and became a really good astronomer in his own right. And these two guys, as kind of a tag team, started observing the night sky with this new telescope. And one of the objects that they pointed at was M31. And this is the defining picture. Now, they had taken a number of pictures of M31 before this, and they were comparing them to this one. But this is the one that showed the change that changed everything. So, if you look up here, VAR, exclamation point, little tiny dot up there. They had found in the Andromeda Galaxy a Cepheid variable, and they were thus able, using Henrietta Leavitt's technique, to determine the distance to Messier 31, the Andromeda Galaxy. How far away was it? 900,000 light years. That's not the modern figure. The modern figure is 2.5 million light years. But the point is this. They figured out that it's well beyond the confines of any plausible size of the Milky Way galaxy. It was way out there. What they didn't know was that there are two types of Cepheids. There's one that's a little dimmer and one that's a little brighter, and Henrietta Leavitt measured one and they measured the other and got the distance wrong. When they figured out that there were two different types of Cepheids, the system was recalibrated, and the modern value kind of slowly evolved to about 2.5 million light years. So how did Heber, Curtis, and Harlow Shapley do? Harlow Shapley, turns out, was exactly right on. Yeah, the sun is not at the center of the Milky Way. He thought it was a little bit closer than it actually is, but he was more or less right. Heber Curtis was wrong. Milky Way is very big, 320,000 light. Milky Way kind of small. I'll give this a tie. They both got it wrong, basically. One overestimated, the other one underestimated it. Heber Curtis was right. The spectroscopy indicated that the nebula were stellar. Van Manen, BS. Heber Curtis wins that one. And you could see dust and gas in the Milky Way. Heber Curtis is exactly right. Milky Way, just like M31. Milky Way, just like M31. That is more or less our view of the universe to this day, at least in terms of the galactic scale. So what we are left with is, yes, there are countless other galaxies. So we have gone from the universe being a bowl over our heads that we can only guess at the distance to. We have gone to maybe the sun being about 18 times the distance to the moon, pretty big. We have gone to the firmament is really far away, but within human comprehension. We have gone to actually knowing the size of the universe, the solar system, by measuring it directly with the transit of Venus, to measuring this distance to the stars, to getting good estimates of the size of the Milky Way based on those initial estimates, to figuring out that our Milky Way is not the only galaxy in the universe. So this is how the universe got big. We figured out how it got big. Took a number of wrong turns, a couple of weird, preposterous ideas about the universe along the way, but eventually, after 2,000 years of working on it, human beings figured it out. And we now know that we live on a planet that is evolving, revolving at 900 miles an hour, et cetera, et cetera. And thank you very much. So, any questions? Yeah. Yes.
When the one problem that epicycles figure doesn't work,
What now?
one problem that somebody should have figured out with the epicycles, even though it fits.
Yeah.
If you kept adding them, right, is that the brightness doesn't change.
The brightness, well, no, with the epicycles you do, with the Venus, it does get closer and further away. And so they did kind of get the brightness. The problem in those days is it's really difficult to make an absolute measure of brightness. You can't, there was no such thing as a photometer in those days.
You never go back and forth.
Yeah. And there's a bunch of other problems with it. One thing is it didn't actually take into consideration the fact that the orbits are not all on the same plane. and that kind of thing. They didn't take into consideration the transits. You know, they didn't know about the transits, but that wouldn't predict the transits from not happening on the far side and happening on the near side. Yeah. So I mean, there was all kinds of problems with it, but a lot of it had to do with the fact that we didn't have telescopes in those days. We didn't have the technology. So technology actually is the thing that moves us along.
Well, they also had the problem that you don't believe your eyes, you believe your logic. Right?
Exactly. Think about it this way. The telescope was the first instrument that improved human senses beyond their natural capabilities. So if you, all until for the entire history of humanity, 200,000 years to today, from the time of modern humans up to today, everything that we saw in the universe was with our own senses. The telescope expanded that. People were skeptical. They didn't necessarily believe that it was telling the truth. And it didn't help that Galileo's telescope was really lousy. It had a lot of optical aberrations. It had this really bad chromatic aberration. And it was really a tiny little field of view. And so, you could look through this and think, this is lying to me. This is not telling me what is really out there. Yes?
The whole thing with the Cepheid or whatever variables.
Yes.
Are they, is it the absolute brightness of each of these, wherever it is in the universe is the same, or?
Yeah, so the period of the variables of the maximum brightness of the variable is in direct proportion to its direct proportion to its absolute brightness. So the amount of time that it takes to go through its sawtooth.
So you can infer from that the absolute brightness in an absolute term. So if you know something looks dimmer, it's further away.
Correct. Yeah. So we got the idea of the distance to the Cepheid variables. First of all, because delta Cepheid is just barely close enough for us to kind of get some parallax on it. Plus the other thing is that I skipped over a lot because I could have gone on for 5 hours and you guys would be really tired of me. But one of the things that they did with figuring out the distances was you could figure out the distance to nearby clusters of stars using parallax, a nearby population of stars, and figure out the parallax to all of those, and then you could see a distant cluster of stars that had the same characteristics, had the same spectral characteristics, it was the same color and everything like that, and you could figure out its distance based on the average of what you figured out by the nearby stars. And so some Cepheids were in distant systems that we were able to figure out the distance to because we knew how far away those stars ought to be, that particular population of stars ought to be. Yeah. So that was how they deduced. I skipped a lot of the steps just because that was a very long talk. I had to cut out about 100 slides, believe it or not. But anyway, they figured it out based on a number of different interesting techniques. But the main one was parallax. So, and nowadays we could get parallax from the ground, like with a telescope through the Earth's atmosphere out to like 300 or 400 light years. That's about how far we can go from the ground. However, there is if you go out into space, where there's no aberration due to the atmosphere, the starlight is very precise, you can figure out much better. And there's a satellite called the Gaia probe. It's put out by the European Space Agency, which can do parallax reasonably accurately out to the distance of the middle of the Milky Way, like 25,000 light years. And so we can get good parallactic distance now to a good chunk of the Milky Way. And then you use other techniques to figure out the distance to other things. So. Anything else? Yeah?
Taking us this far, to me the next step is the expansion of the universe.
Correct.
Is that, I guess historically, is that like Einstein's redshift, or is there anything before that we started?
That's talk number 2. That's the 20th century. The expansion of the universe allows us to measure the distance to the furthest galaxies. The next thing that Hubble did with Milton Humason was to start to measure the redshift of galaxies. And he noticed that the further away galaxies get, you can deduce the distance to galaxies from a number of different ways. For the closer ones, you could do Cepheid variables, and then the further ones, you used other relationships, like the average brightness of the brightest star in the galaxy and that kind of thing. They did a number of different techniques, but the nearby galaxies that he did this to, he and Milton Humelson's really big project was to eventually figure out that the further away you got, the faster things were flying away from us, which seemed to imply that the universe was expanding. And as we got better and better at seeing stars and further away galaxies, that was in fact the initial mission of the Hubble Space Telescope. That's why they called it the Hubble Space Telescope, was to see Cepheid variables in much more distant galaxies. The first one they ever did it for was Messier 100, which was in the Virgo cluster, 65-ish million light years away. That was its mission, was to calibrate the expansion of the universe that Milton Humelson and Hubble initially got started. They figured out that there was expansion, and the Hubble Space Telescope helped calibrate that. Now, this is getting all thrown into whack because now we've got dark energy, which is actually causing the universe to expand a little bit faster than we think it ought to. About 7 billion years ago, the universe started to pick up speed, and that sort of throws it into a problem. But yeah, that's another portion of it. So. Anyway, thank you guys. I really appreciate you sticking around.
Okay, we're gonna start in about 10 minutes, we'll start part 2.
Only kidding. If you want me to do a part 2, I'll do it next year. Okay.